So we're going to start this chat about radian measure with a little conversation about arc lengths. So this idea is just trying to find the length of a chunk of a circle. So I'm going to attempt to draw one for you. Here we go. Hopefully that turned out okay. I'm looking at it from the side, so it may be a bit skewed. So what I'm going to do here is I'm going to tell you that this circle has a radius of 2, and what I'm after is the length of the arc just in here. I only want this piece, and that much makes 60 degrees. So if I wanted to figure that out, the first thing I should probably think about is how much the circumference of this whole circle is. So to do that, I start with the circumference of the circle, which is 2 times pi times the radius. So for this particular circle, the circumference would be 2 times pi times 2, which is 4 pi whatevers. If this is in feet, then this is in feet. If this is in meters, this is in meters. If it's unitless, then so is this. So I'm just going to leave it like that. Now that that's done, I have this wedge here, and basically I'm erasing the entire circle and asking only about that chunk there. How long is that? So the word that we're going to use for that is an arc. So this blue thing, this is an arc. Subtending, there's a $10 word for you. Subtending 60 degrees on an r equals 2 circle. ... So arc basically is it's a chunk of a curve. I've specified that the curve is a circle here. I've specified the radius of the circle, and I've told you that this chunk is 60 degrees of that circle. So if I want to get the length of that thing, I need a new symbol. It's not the full circumference, it's just an arc. And the letter we're going to use for arc and for arc length is an S. You know, it's a natural choice using an S for the word arc length, but it is what it is. So this chunk here, that is some piece of this circumference. It's not the whole thing. It's just a little fraction of it. So the way I'm going to get that fraction is I'm going to take the angle that I have there. It's 60 degrees out of a total of 360 degrees. So the whole thing was 360 degrees. This chunk is a 60. So that fraction, 60 out of 360 multiplied by the full circumference, should give me my arc length. Now it looks a little complicated there. So I'm just going to reduce that fraction. 60 divides evenly into 360 6 times. So this fraction is the same as 1/6 of 4 pi. So it's a little easier to see there. This circle had a circumference of 4 pi, and 60 degrees is 1/6 of a circle. So the arc length of just this blue piece must be 1/6 of the full circumference. That's all we're doing. Is you get the circumference of the full circle, and then you take some fraction of it in order to get just this little arc there. If you like, you can reduce that further. 4 pi times 1/6 is 4 pi over 6. And 4 and 6 both divide evenly by 2, so that reduces to 2 pi over 3. Now, you may be compelled to type that into a calculator. To do 2 times pi is 6.28, and then 6.28 divided by 3 would give you 2.9-ish something. around there, you can do that, or you can just leave it like that. This actually turns out to be the superior answer because it didn't require any rounding. That is exactly the arc length of this chunk, 2 pi over 3. So if you can get used to seeing a number like this and having a rough idea of what it's worth without rendering it as a non-repeating decimal, you'll be better off. Okay, so now that we've done this, I'd like to take this thing here and I want to make it like a formula so that we have something that we can work with a little more easily. So I've got S for the arc length, and I have 60, which was the size of this angle. So I'm going to use an alpha for the size of that angle. And it was divided by 360 because there are 360 degrees in a triangle. By triangle, I mean circle. They are not the same. There's 360 degrees in a circle, so that's why we have that there. 4 pi was the circumference of this circle, and you get the circumference of a circle by doing 2 times pi times the radius. So I'm just going to write that in here like this. And if I were to rearrange this a little bit so that the angle and the radius were together, because those are our variables, and the constants were together, I'd end up with S is 2 pi over 360 times alpha times r. So there we go. I'm going to put this in a box. And we're going to call that the arc length formula. All right. So I'm just going to do a few examples where we try and solve for an arc, and then we're going to try and solve for an angle, and then we're going to try and solve for a radius. But I'm going to have to clean this off first. So I'm going to clean it off, and I'm going to move this up here so that it's just sitting in front of us as we work. So I put our arc length formula up there. I forgot just a minute ago that 2 pi over 360 reduces to pi over 180. So I'm just going to do that up there. Then I'm going to calculate the length of an arc subtending 40 degrees on an r equals 5 circle. So as with all geometry problems, when you read a sentence about a shape, you better draw the shape. It's just going to make your life easier. So if I were to do that, get myself a circle here. Hopefully that's okay. And I'm going to acknowledge that the radius is 5 whatever. And I'm after an arc subtending 40 degrees. So I'm just going to pick a random place to draw my reference line. And then I'm going to draw something like that and acknowledge that that's 40 degrees. So what I'm after then is just the length of this little chunk. So using the arc length formula then, S equals pi over 180 r alpha. I don't know what the arc is. That's what I'm trying to calculate. Pi is just pi. 180 is just 180. The radius of this particular circle is 5. And the angle I'm subtending is 40. So I get all that in there. Right. 5 times 40 is 200 pi's over 180. So I'm done at this point. That's an answer. It's the correct answer. It's not in a form I like. It's grammatically it's sort of rude to not reduce your fractions. So I'm going to work on that. These are both divisible by 10. That would give me 20 over 18. Those are both divisible by 2. So if I were to divide by 20, I would get 10 10/9 of pi. Whatever that is, 3.45-ish. So you could do 10 times pi divided by 9 and spit this out as a decimal, or you can just leave it as that. And I would prefer you to do that, and it would be best for you to get comfortable leaving it like that, so that you don't have quite so many rounding errors as we go forward. Okay, so I'm going to clear this off, and we're going to try solving for r. So how large must the radius of a circle be for a 75-degree arc to be 18 pi long? So again, it's a sentence about a shape, so I better draw it. Let's get hopefully that turned out. Okay, radius, I don't know. I'm going to pick a random reference point here. How about that? 75 degrees is less than a right angle. That's 75 degrees there. And this piece here, from here to here, is 18 pi units. Okay, so what's happened in this one is I was given the arc length, that's 18 pi. I was not given the radius, but I was given the angles at its subtends. So I just need to plunk those things in and do a little bit of algebra to work it out. So 18 pi, wait, I'm going to write the equation down for you. S equals pi over 180 r alpha. The arc length I was handed was 18 pi units. I don't know the radius of the circle, but I do know that it's a 75-degree arc. Okay, so I have a little bit of work to do. First off, I'm going to notice that I have a pi on this side and a pi on that side. And those two things, if I divide both sides by pi, now they're gone. I can multiply both sides by 180, so that would give me 18 times 180 equals 75r. 18 times 80, 18 times 18. I'm going to calculate that. I think it's 324. Yeah, 3,240. And I'm going to divide both sides by 75. So both of these numbers divide by 5, so I'm going to do that. 3240 divided by 5 should be 648. 648. 75 divided by 5 is 15. Both of these numbers divide by 3, so 648 divided by 3 should be 216. 648 divided by 3, 216. And 15 divided by 3 is 5. So the radius of that circle would have to be 216 fifths. Now if you wanted to, you could render that as a decimal. It'll be 43.2. So in order for that arc to be that big, the radius of the circle would have to be 43.2 units. Basically, you just dump the numbers in, and then you use your algebra skills to isolate the variable that you don't have. So we're going to do that one more time with the angle. So let me clear this out for you. All right, what angle is subtended by an arc that is 8 pi long on an r equals 10 circle? So I'm just going to draw it for you. Circle And then I've got r equals 10. And I have some arbitrary angle in there. I don't know what that is. But I know that from here all the way around, this blue section there is 8 pi units. So I'm just using this arc length formula. Pi over 180, r alpha. And the length of this arc is 8 pi. And I've got pi over 180, which is annoying that that constant is there, but whatever. The radius is 10, and alpha. Okay, so I'm going to note that there's a pi on both sides, so divide both sides by pi, and that is gone. I'm going to multiply this side by 180, so I end up with 8 times 180 equals 10 alphas. That'd be 80, 124. Well, that's neat. Times 180 is 1,440. Yeah, okay. 1,440. Divide both sides by 10, I get 144 equals alpha. So that arc would have to be 144 degrees in order for it to be 8 pi units long on an r equals 10 circle. Okay, so I don't know if you've noticed, but we've had this irritating pi over 180 stuck in front of our arc length all this time. And that's because there are 180 degrees in half a circle. So we're using this idea of degrees in order to figure out what fraction of the circle we're working with. So a question then to you is why are there 360 degrees in a circle? Because that feels like a dumb number. It's not 100. If it were 100, then that would fit with the metric system, right? You cut things up into 100s. Even if it was cut up into 1,000s, that would make sense. If you go back to the imperial system, right, which seemed to be based on 16, 16 doesn't go evenly into that. Some of those, there's 12 inches in a foot. There's a 12 in there, but that's 30 sets of 12. It doesn't make a lot of sense. And I think if you were to go research it, you would find it has something to do with shadows in like Babylonian or Sumerian times, where if you put a stick in the ground, any place between the two tropic lines on Earth, as the seasons shift, the shadow of that thing will precess around this particular post you have stuck in the ground. And it's not a coincidence then that there are 360 degrees in a circle and 360 days in a year. That's where that number comes from. So I don't know about you, but I'm not particularly interested in continuing to write constants down just because some people 7,000 years ago were using sticks stuck in the sand in order to count a calendar. So we're going to make a little change here. We're going to stop using degrees, and we're going to start using a thing called radians. So I'm going to erase this, and then we're going to talk about how that works. So what I'm going to do is I'm going to take a full circle and I'm going to chop it up into chunks, like these little wedges that are equally spaced. In this top one here, I'm going to do 45-degree increments. So 0 to 45, 45 and 45 would be 90, 90 and 45 would be 135, 135 and 45 is 180, which is half a circle, which is where it landed, so that's good. 180 and 45 would be 225, 225 and 45 is 270. 270 and 45 would be 315. Okay, so far so good. And an additional 45 would get this to 360 degrees, which is all the way around. On this one, I'm going to cut the circle up into 30-degree wedges. So if I start here, 0, then 30, then 60, then 90, then 120, 150, 180, which landed at halfway, so that's good. 210, 240, 270, 300, 330, and 360, which is full circle, so that's good. So the idea here is that I don't actually need degrees. I don't actually need to measure the size of the angle at all if I can just measure the length of the arc out here. Because if I were measuring the arc directly, then I wouldn't need this constant, and that would simplify everything a lot. So how am I going to do that? Well, first, I'm going to just look at how much of a circle each thing is. So I'm going to pick an angle at random. I'm going to pick that one, 225. 225 degrees. So if I look at that, if I started here, I've cut this circle into 1, 2, 3, 4, 5, 6, 7, 8 pieces. And 225 takes up 1, 2, 3, 4, 5 of them. So 225 degrees is 5/8 of a circle. So don't call it 225 degrees. Call it 5/8 of a circle. And then you don't have to worry about this conversion factor that I just erased there. If you pick another one from up here, let's say 45. 45 would be 1/8 of a circle. So picking one down here, 120 degrees. Well, this circle's been cut up into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pieces. And 120 takes up 1, 2, 3, 4 of them. So 120 degrees is 4/12, which happens to be 1/3 of a circle. And if I pick another one, let's go with 330 here. 330 degrees happens to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 twelfths of a circle. So I don't need to have degrees at all. I just need to be measuring how much of a circle I'm using up. So I can even make this more specific, right? Of what circle? Which circle would you like me to use? And the idea is that if I use a circle with a radius of 1, then I can just scale it up later, right? If I want to have a radius of 3, then I would just have to triple this. If I wanted a radius of 10, I'd have to multiply these by 10. So if instead of a circle, I erase that and I replace it with the circumference of a circle with radius 1. So circumference is 2 pi r. If the radius is 1, the circumference is just 2 pi. So if I go through and I do that, replace of a generic circle with this specific reference circle. Let's see, what do I end up with there? Well, this 2 divided by 8 ends up giving me 5 pi divided by 4. This 2 divides that 8, which gives me a single pi over 4. This doesn't reduce, so it'll look like 2 pi over 3. And this 2 here divides that, gives me 11 pi over 6. Okay. So these are lengths. This number here, 11 pi over 6, is the length that it takes to go from this point all the way around to there. So this is an arc length. The length of the arc on an r equals 1 circle subtended by 330 degrees. Okay. Now, how does this make your life any easier? Well, first off, these numbers, like 11 pi over 6 or 12 pi over 6, that's 2 times pi, that's about 6. So I've scaled down my units. Instead of taking 360 degrees in order to get all the way around a circle, I'm only taking up 6.28 whatevers in order to get all the way around. So that has shrunk my scale down. So that's encouraging. Also, almost every angle problem you've ever done in trigonometry, you needed the units to be in meters or feet or whatever, so that you ended up with lengths popping out instead of degree lengths. So this conversion here has stripped out the degrees entirely and left you with a sort of nice unitless feature. So we're going to call these things radians. So if you're choosing to measure an angle by the length of the arc it makes instead of the size of the corner down here, you are measuring that angle in radians. And if you are going into physics or engineering or math of any kind, you will be using radians. You're going to abandon degrees very shortly and work in this specifically. So what I've got up here is just the quick conversion factor, right? 225 degrees is 5 pi divided by 4 radians. Or you just say that as 5 pi over 4. 45 degrees happens to be pi divided by 4 radians. So I guess basically I just need to go through and I need to identify these angles in terms of radians. So I'm going to clear this off and we're just going to make a list. Okay, so from this up there, I'm going to split the numbers into 2 different lists. I'm going to go with 0, 180, and 360. And then I'm going to go with 90 and 270. And then I'm going to do 45, 135, 225, and 315. So 0 degrees should end up being 0 radians. That's pretty easy. If I go to 180, I have done 1, 2, 3, 4 out of 1, 2, 3, 4, 5, 6, 7, 8. So that's 4/8 of the full circle. Now 4 times 2 is 8. 8 divided by 8 is just 1. So that leaves me with 1 full pi worth of radians. I'm going to move these over so I have some space. .360 would be 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 8 of that reference circle. But 8 divided by 8 is 1. 1 times 2 is 2 pi. So if I get rid of the in-between steps there, I have 180 degrees being equivalent to 1 pi radians, so 3.1415926. 360 degrees is 2 pi's worth of radians. So in here, 90, to get to 90, I've done 1, 2 out of 1, 2, 3, 4, 5, 6, 7, 8. So 2 out of 8 multiplied by the reference circle. 2 times 2 is 4. 4 divided by 8 is a half. And a half times pi would be a pi divided by 2. 270 would be 1, 2, 3, 4, 5, 6 out of 8 times my reference circle. 2 times 6 is 12 over 8. Both of those numbers divide by 4, so that leaves me with 3 pi divided by 2. So you're maybe starting to see why I grouped them this way. 0, 180, and 360 are whole values of pi. If I get rid of the intermediate work here so it's not quite so cluttered, .90 and 70 are half pi values. So 1 half of a pi or 3 halves of a pi. If I go to 45, 45 is going to be 1 out of 1, 2, 3, 4, 5, 6, 7, 8. So that's 1 out of 8 multiplied by my reference circle. 2 times 1 is 2. 2 out of 8 is the same as 1 over 4. Let me write that. 2 out of 8 pi. This reduces to 1 over 4 pi, which is pi over 4. Okay. Now I don't want to calculate this over and over and over again. I'm just going to use patterning. If this thing is 1/4 of pi, then to get here would be it would be 2 of them. 2/4 of pi. You know, 2/4 is the same as a half. So that's nice and consistent. To get to here, I've had to do 1, 2, 3 chunks this big. So 135 is going to be 3 pi's out of 4. I get rid of this so it's not so cluttered. In order to get to 225, I had to do 1, 2, 3, 4, 5 chunks this big. So 225 is going to be too close to that one. 225 will be 5 chunks this big. And the last one, 315, would be 1, 2, 3, 4, 5, 6, 7 chunks this big. So 7 pi over 4s. So I'm just cutting the circle up into a certain number of chunks, assigning the size of the first chunk, and then just counting up the number of those chunks in order to determine the size of the angle in radians. So if I do that down here, 30 degrees, that's 1 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So a 30-degree wedge is the same as 1/12 of my reference circle. 2 times 1 over 12 would be 2 pi over 12. Both of those numbers divide by 2, so I get pi over 6. Okay, so that's my basic wedge. The next one, 60 degrees, would be 2 of these. My next one, 90, would be 3 of them. My next one, 120, would be 4 of them. The next one after that, 150, would be, don't use an equals to it, would be 5 of them. And 180 would end up being 6 of them. Now, some of these fractions reduce, some of them don't. So I'm just going to hunt for the ones that do. Pi over 6 doesn't reduce. 2 pi over 6 is the same as 1 pi over 3. 3 pi over 6, so both of those numbers divide by 3. So that reduces to a pi over 2. And that's encouraging because we saw that value show up here. It's nice and consistent. 4 pi over 6, both of those numbers divide by 2, leaving me with 2 pi over 3. 5 pi over 6 does not reduce. 6 pi over 6 does, leaving me with just the pi. 180 is pi radians. And that's also good because we had that appear up there. So if you were to continue this pattern, you'd see that 210 was 7/6 of pi, which doesn't reduce. 240 is 8/6 of pi, which would reduce to 4 pi over 3. You should write that down if you need to. 270 would be, what are we counting here? 8/6, 9/6 of pi. 9/6 of pi reduces to 3/2 of pi, which is good. That's what we had there. This is 10/6 of pi, which reduces to 5 pi over 3. This is 11 pi over 6, which does not reduce. And this would be 12 pi over 6, which reduces to 2 pi, which again, we got back to. So this is what's going to happen from this point forward. Instead of saying something is a 60-degree wedge, we're going to label it as pi over 3. So there are no degrees anymore. You will have to find on your calculator to make sure that this display says rad, R-A-D, for radians. And then all of your trigonometric functions are pre-calibrated to this particular measure because it does turn out to be superior once you get into a higher level of mathematics. So I'm going to clear this off, and I'm going to get some special triangles on here, and we're going to try and do some work with these angles in radians.